Hello everyone, my name is Joykirat Singh and today I will be presenting the paper Data-scarce Behavior Editing of Language Models. This work has been accepted in EMNLP Findings 2025. So what's the core problem that we are addressing here? We know that large language models are incredibly powerful. They are trained on vast amount of text on the internet, which allows them to solve a wide range of tasks. But the internet is a messy place. It's full of noises, biases, and irrelevant information. As a result, LLMs learn spurious token association. This leads to a well-known issue that we have already probably encountered. For example, they can hallucinate or just make things up. Their performance can be very brittle, meaning a very small change in a prompt formatting can cause a huge drop in accuracy. And in some cases, they can even generate harmful or toxic text. The traditional way to fix this is via supervised fine-tuning, but this approach is often data inefficient and can lead to a phenomena called catastrophic forgetting, where the model gets better at a specific task but loses its general capabilities. So the central question is of this paper is, can we correct a model's bad habit by using only a handful of examples and without having to retrain it completely? So moving on, the key insight that we got from this paper was we don't have to retrain it, we just have to rewire. So we build on two important findings from recent research. First, that within an LLM, the effective generalizable neural circuits actually coexist along the noisy and problematic ones. Second, fine-tuning doesn't really teaches a model new skills. It mostly just enhances or suppresses the ability it already has learned during training. This leads to a new idea that instead of trying to override the model knowledge, what if we could directly intervene in its internal mechanism? The goal would be just to amplify the good circuits and quiet down the bad ones. However, this possesses a huge challenge. That manually finding these exact neurons responsible for a certain behavior is incredibly complex and gets exponentially harder as model gets bigger. And it does not go very well with scale. And that brings us to the solution that we want to propose in this paper. TaRot, which stands for Task Aware Rotation. The core idea of TaRot is that inside a transformer model, attention heads are constantly reading from and writing to the residual stream, which is like the model's working memory. These heads learn to associate certain inputs token with certain output tokens. The problem is that each head's learner learn many associations, which are stored in what's called a superposed state, like multiple memories packed in one space. Tarot takes a much more nuanced approach here. Instead of turning heads off, it applies a learnable rotation matrix to their output. As you can see in the diagram, if an attention head output vector h is pointed toward an undesirable token, the TaRot learns a rotation operation r theta to gently steer it towards a desirable output, that is the blue dots. This allows us to make a fine-grained adjustment without destroying all the other useful information stored in the head. So how does TaRot actually works? Like what is the mechanism? So first, for a given task, TaRot introduces the small parameterized rotation matrix into the attention block, specifically focusing on the initial layer of the model where most of the pre-trained knowledge exists. Second, it needs to find the best rotation angle for the task. Instead of using gradients, which would require backpropagation, TaRot uses Bayesian optimization, that is a gradient-free method that can efficiently search for the optimal set of angles. And third, the whole optimization process is extremely data efficient. It only requires between 6 to 20 labeled examples per task, which is on par with standard few shot prompting, which makes it a very practical use for real world applications. So, what is the experimental setup that we used? We tested TaRot on 6 different instruction tuned models with a wide range of sizes, from 1.5 billion up to 32 billion parameters. This includes popular models like Qwen 2, Phi 3, Mistral 7B, Llama 3, 8 billion. We also evaluated on 4 classification tasks that test different abilities, from world knowledge to logical reasoning, and 2 natural language generation tasks, generating positive IMDb reviews and detoxifying text. Finally, we compared TaRot against several strong baselines, including the base model zero shot and few shot performance. other editing methods like eigenpruning and a crucial ablation we call rescaling, where we simply scale the output of attention hits up or down instead of rotating them. Across almost all models and tasks, TaRot was consistently the best or the second best performing method. In the zero shot setting, where the model gets no examples, TaRot achieves an average performance improvement of 15.6 over the base model. It also worked in the few shot setting, where the base model was already given in context examples. TaRot still provides an average boost of 14%. This shows that its improvements are complementary to the in context learning. TaRot was able to improve both the task-specific scores, like making a review more positive, and the fluency of the generated text. The rescaling baselines, on the other hand, sometimes achieve a higher task score, but they did by producing unnatural, less coherent text. This should suggest that rotation is more surgical invention, while rescaling is more like a sledgehammer. So why does rotation actually works much better than rescaling? It goes back to our intuition that since knowledge in attention head is superposed, the fine-grained control offered by rotation is much more crucial for redirecting models' behavior without causing any collateral damage. We also perform two key ablation studies to really stress test our method. First, we confirmed the hypothesis about layer selection. We experimented with applying the rotations to different set of layers and found that intervening in the first half of the model consistently yielded the best performance with the fewest parameters. Second, we tested TaRot's robustness to prompt sensitivity. We created three different system prompts for the same task. As expected, the base model performance fluctuated significantly depending on the uh, prompt. TaRot, in contrast, not only improved the overall score but also dramatically reduced its variance, making the model performance much more reliable and less brittle. So to conclude, TaRot is an efficient, gradient-free, and highly data-efficient method for editing the behavior of language models. By applying parameterized rotation to attention head output, it successfully corrects undesirable behavior without needing the intensive manual effort for localizing circuits or requiring large task-specific datasets. It provides a robust and consistent improvement across a wide range of models and tasks, which makes it really practical alternative to both model engineering, to both prompt engineering and traditional fine tuning. Few of the limitations include that it can only refine abilities the model already has. It cannot be used to inject entirely new knowledge or for domain adaptation. And since it requires direct access to model weights, it cannot be used on closed sourced API based models. Future work could focus on developing a more formal theoretical framework for these interventions and, importantly, exploring ways to prevent potential misuse, such as using it to bypass a model safety alignment. Thank you.